Good morning, ladies and gentlemen. My name is Michal Jandera. I'm from the Czech Technical University in Prague, and I will present a parametric study of stainless steel slender I-section beams, work made mainly by my PhD student, Marek Sorf, so credits to him. I will start with the design rules for stainless steel beams subjected to lateral torsion and buckling. I will briefly show our beam tests, a model validation, and a parametric study of stainless steel beams. And I will show also the comparison with the results of the study and proposed modifications. In the Eurocode 3 part 1 part 4 there are design rules also for members subjected to lateral torsion buckling. It's that there is a reduction factor KLT for this type of members and this phenomena. It's quite similar to the specific case in part 1.1. There are only two curves, two imperfection factors, 0.34 for cold formed and hollow sections and 0.76 for open welded and other sections. We have made also a comparison to the proposal of Taras and Greiner for H and I sections. This proposal is now part of the pre-norm Eurocode 3.1.1. It's a slightly modified lateral torsion buckling curve, where also the imperfection factor is a function depending on the ratio between the weak and strong axis section modulus. Quite recently, and partially in parallel with our research, there was published a study and recommendation for stainless steel beams subjected to lateral torsion buckling by Fortan and Rossi from Q11. They are focused on hot rolled sections, so IPEs and H profiles, and they were focused on all three common stainless steel families. Their findings are that the proposal of Taras and Greiner could be used also for stainless steel members if the constant of imperfection factor are modified. So they proposed different constant for different stainless steel family. We wanted to complement to this research, so we have focused mainly on slender cross sections, which were not covered by tail study, and we have focused on welded section beams. The slender sections are also part of our research focused on local buckling, but that's not the topic for today. Today I will focus only on lateral torsional buckling. The tests were 4-point bending tests using this setup on the picture. So at the point loads, lateral and torsional buckling was prevented by the restraints illustrated in the picture. Of course, material properties were measured beams were fabricated from ferritic steel and austenitic steel. So the blue curves are for the ferritic material, the red curves in the diagram below are for austenitic steel grade. Imperfections were measured, residual stresses were used as recommended by Yuan Wang, Shi, and Gardner for welded cross-section. Here is the comparison between the test and final element model. The prediction of the failure mode is shown on the right hand side, and the difference between the prediction of the model and the test was for members subjected to lateral torsional buckling below 5%. Later, we have extended the results by a parametric study. The parametric study covered all the three common types of stainless steel, so austenitic, ferritic, and duplex. The material properties were considered as sort of average for this type of product by the recommendation of Afshan, Zhao, and Gardner. We've considered a three section aspect ratio, so height to width from 1 to 3 ratio, 48 cross sections, class 3 and class 4, uniform bending moment, and of course different slenderness for lateral torsion buckling. And later we've added also some limited number of simulations for non-uniform bending moment and for stocky class 1 sections. I will not show all the comparisons in chart, only summarize that the Eurocode 314 led to relatively good prediction. There were some slightly unsafe results for lower slendernesses and more conservative results for higher slendernesses of the beam. We've observed better prediction with the proposal of Taras and Greiner, lower deviation of the results, and clearly need for different imperfection factor for stainless steel members. Finally, we were able to confirm the recommendation of Fortan and Rossi regarding the constant in the imperfection factor. Additionally, we were also able to set an upper bound value for this factor, different for austenitic steel, where the nonlinearity of the stress strain diagram is higher, and different one for duplexes and ferritic steel grades. Here is a reliability study summarized in tables, only showing that the safety factor was below 1.1 for all three stainless steel grades, and also for lower slenderness range, mid-range slenderness range, and high slenderness range of the beams. Later, we included a smaller study on moment gradient influence on the reduction factor KLT. It is now expressed by factor Fm in the pre-Eurocode 311. So that's the formula which was used. We've made a smaller study at first to see where the formula may lead possibly to some unsafe results. So this was a stocky class 1 section from austenitic steel and age section. We've considered different moment distributions, so like linear moments with ratio 1 to 0.25, 1 to 0, minus 0.25, minus 5, and also uniform distribution of the load along a supported beam. Here is the comparison. In the chart above, all the points are significantly above 1, and this is a comparison neglecting this factor Fm, whereas below we use this factor Fm, and it clearly leads to less conservative but still safe results. To summarize, I've shown a numerical model which was validated on tests, and later the numerical data were generated in a parametric study focused mainly on class 3 and class 4 sections. We have observed a good prediction of the procedure published by Taras and Greiner, and with imperfection constants or imperfection factor constants proposed by Fortan and Rossi, where we have included also some upper bound limit for this factor. And finally, we have checked that the applicability of Fm factor in pre-Eurocode 3 part 1.1 is safe also for stainless steel beams. Thank you very much for your kind attention.